course materials folder. Newtown put this document that's got all sorts of useful like conversions and units and equations and stuff. And then there's this one that shows some examples of like how to lay out problems and everything. So if you're not sure how you're supposed to be doing stuff, by now you should though, but there's some resources for you to take a look at.
You guys remember I have 2 rules, right?
Yeah.
What is it?
Number 1, ask questions. Number 2, go back to number 1.
Simple. So if you're confused about something, just ask. You know, which reminds me, what was the there's a screw up in the lab example? Oh, it's kilogram 9,960 kilograms per meters cubed was the reference density or calculated density. It's actually 996. Don't ask me where the 0 came from. There's probably a decimal point missing in there.
Put zeros in front of your decimals. I don't know what math teachers or K through 12 people told you to stop doing that.
Yeah.
But it pisses me off. Put zeros in front of the decimal. Well, because the decimal gets rubbed off.
Oh, it's
Now 0.2 becomes 20.
I don't know
Right?
either. Don't get me wrong. But yeah.
Well, you don't say 0.2. You just said 0.2. So you think that way.
Yeah.
Think in language. So you think 0.2. You're right.
Again, it's an engineering standard
Still.
that we try to do. Okay. So we will teach you by the time you leave here to have some semblance of a profession. And if we can do that, then we've probably done everything else we can do, and there's no more to do to you. Okay, so we're moving into hydrostatics. Okay, so this is the area where we start discussing pressures, manometers, pressures on surfaces that are submerged. It's a great example I use. Is actually, what is the pressure on a plate glass on the bottom of an aquarium? And I'm thinking to myself, who in the hell builds an aquarium where you look up at the fish? Okay, seriously, it's a great example because it wants to calculate the pressures there and what the forces will be and all that fun stuff. But literally, no way in hell.
I saw one in Facebook Reels yesterday.
Did you?
Yeah.
Yeah,
It was this inner window thing so the cat could get up there and watch the fish.
I don't want to be the engineer that does that with, hundreds of thousands of gallons of water over top of me. I'd rather have it done in a glass tube because circular circumference of things hold more pressure than flat surfaces do. But it's
I think so.
yeah. All right. So anyway, we're going to deal with pressure today. So and this didn't change any. It's a force. It's a force acting on an area. Anybody remember the lovely equation? Yep. No, seriously. M over V?
That's not right.
No. Force over area from statics? I know it's been a while for some of you, but do yourself a favor and go back and review some of that stuff. It's going to come back to haunt you. All right. Units, pounds per inch squared, Newton meters, and we could wind up with pascals, okay, or even kilopascals, but somewhere in there. Now, the interesting thing is, and this is going to sound really dumb and basic, but if I have a cube and I stick in some water, P, 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 and that defines a cube. Then I can have a sphere. That's a really crappy sphere. let's do this. We have shapes. Cool. Go away. And I put a pressure on it. Or if I have a point, it will be the same pressure. Okay. Now, why do I bring that up? Because if you remember back in statics, it always say, we have this little element. And they used to draw these little squares in there, and they'd say, what's the stress on this element? And it's this little mystical thing in the center of nowhere. Okay? But it's just a point. They usually use it as a square just to identify where the forces are on it. The reality is this. Depending on the size of these geometric shapes, the pressure is going to be different in one place than on the other. Okay? But when I'm telling you that the pressure is the same at this point in space, it's all the same all the way around at that point in space. Okay? But it could have that shape. It could be a circle, it could be a cube, okay? Are you okay with that? Okay, so don't get hung up on, well, I'm going to show you something in a minute here that happens to be a submarine, and the pressure at the bottom of the submarine is not the same pressure at the top of the submarine. Okay? And that would be problematic. And it's also, if we think about a diver going down at certain depths, the pressure at his helmet is different than the pressure at his boots. Okay? All right. So all right. So we have a submarine in the ocean, and we have a pressure on it. Okay? And it's at some depth down here, and we're going to label it a Z for now. We'll change it eventually to, we'll start using H, but Z is a good mathematical way to think about this as you're doing things. Okay? I guess I should draw some arrows here. Okay, and we're going to be able to figure out what's going on at different depths based on some of these laws. So far with me? Now, while you're all keeping that up, I told you there's two types of engineers in the world, right? Those who make targets and those who make weapon systems. Well, I'm a mechanical engineer. I make submarines. You guys make targets. Okay. Funny thing is mechanical engineers make boats too, or naval architects do, and the whole reason for a submarine is to sink a boat. You know, submarines don't usually sink things on land, but generally we're there. So far, looks like everybody's caught up. Okay, I'm going to slide that up just a bit. We'll leave you some space there. We got a couple of laws we got to play with. First law is Pascal. Okay, so pressure is going to equal or act equally in all directions on a small volume of fluid. So that's why I went from that cube, the sphere, to a point. Those cubes in that sphere are representing some point on that depth on the surface of something. Okay, but ideally, it's really acting at a point. Okay. All right. The second law, or the second part of this. That dash doesn't need to be in there. What was I doing? Okay, so pressure will act perpendicular to its boundaries. So this is really cool. First one explains Pascal's second law. The diagram to my left, your right, actually discusses a lot of things we're going to do with submerged surfaces. Okay? And we're going to have some fun with that. Well, I'll have some fun with that. I shouldn't speak for you, but you'll have some fun with it. If you're not having fun, let me know, though. Right? We want to have some fun. Hopefully. All right. Now, what happens if the shape changes? Because, you know, we're humans. We like to make weird things. So this side all stays the same. But right here, things get a little wonky. So in that corner, it's still perpendicular, but we're perpendicular to a curve. Anybody go through all the math and never figure out why you do all the stuff you do in calculus? This is the reason. Okay. We're looking at an infinitely small particle on that surface that force acts on. Okay. And it'll be perpendicular to that. Okay. Now, the one we really like to play with in civil is this. is we like to look at dams. Okay? I can't think of a greater civil engineering project than a dam. Okay? And they're never just a vertical wall. I had to, Brian Terrell, I had a discussion with him about doing a concrete masonry form. Sorry, it was a styrofoam, so anyways, the styrofoam building blocks for a wall, 30 feet tall. And I looked at it, it's like, huh? Gotta be some limits to that. I get all the forces are pretty much going downward. But wind loads? 30 feet of concrete going in the air, that's a little sketchy. It's like, what braces you're building in? Well, I gotta work that out yet. It's like, I hope so. Even if you put 8 feet of it in the ground, that still puts 22 feet above the ground. It's like, okay, great. You tie the rafters on the top of this wall, and you get the rafters for the trusses. And you get cross ties at the top. It's still, you can wrap concrete around it. Not what I want to do. But generally, water, same thing. Hoover Dam is actually at the top is 400 feet wide at the top, but at the bottom, it's something like 900 feet. So it tapers outward this way, straight down this wall, but it's got a lot of concrete down here to hold up all that pressure on this side. Okay? So keep that in mind. All right. The other fun thing with pressure and containers is this. Yeah. I hate it when a drawing doesn't come out. Actually, what I do hate is the new surface does not draw as smoothly as the old surface did for angled lines, and I don't know why. Pisses me off. So the pressure at an equal depth, no matter what the container looks like, is the same. So basically what it says is shape doesn't matter. Okay? So literally, if I have a reservoir that's 400 feet in the air, and I go to another reservoir that the bottom of the pressure at this higher one could be the same pressure as what's down below at its equal depth. Okay? One thing's going to change is we've got atmosphere, or not atmosphere, we've got the earth involved. But ideally, as long as the depths are the same, it's the same pressure.
But they need to have the same volume of liquid.
Nope. Doesn't matter on volume whatsoever. Shape, volume, nothing. All it is depth. So, Death Valley. Everybody know how far Death Valley is below sea level? It's deep. Okay? So, Death Valley has higher pressure, but that pressure is the same all across that. It's the same pressure as if you went someplace else and took away the water and went out to Catalina Island off the shore and took all the water away. Death Valley and the depth, equal depth on the planet off Catalina Island would be the same pressure. 14.7, so it'd be probably 13.8 or something. And it's enough to make a change. Okay? Doesn't matter on shape, doesn't matter on a lot of things. Okay? It's just elevation changes pressure. Okay? All right, while we're playing with this, and yeah, we've been playing with water because that's what you guys do, but I want you to get a handle on pressure. So, pressure in Denver, Colorado, for air pressure is lower than pressure at sea level. And the reason they call it a mile-high city, because it is literally 5,200, and I don't think it's 80 feet. It's actually like 57 feet or something, but close enough. No one's going to dispute it, or at least their claim. Which, by the way, you can claim anything, and if people buy it enough, they believe it. So pay attention to what you think you know and what you've been told over the years, and question it without fail. Okay? Just because someone who stands up here and has got a professional engineering license says this is true, you shouldn't believe me. Okay? Because you're going to fall for stupid shit.
Yes, sir.
Say that.
Will not believe you.
You don't want to fall for dumb things down the road. Prove it to yourself. Be curious enough about your profession to make sure it's right. Okay? But yeah, people have been claiming it's mile high, but I don't think the elevation is quite someplace in Denver. I'm sure it's exactly 1 mile, but I'm not sure the whole city is. It's in a great big hole. Airplanes. So as we move in the air in an airplane, pressure gets less the higher we go in the atmosphere. Which is why we have to pressurize the plane so that you can breathe naturally. Otherwise, everybody would be wearing oxygen masks the entire flight, and the amount of oxygen needed would be ridiculous. It's also why B-17 bombers and B-24 bombers in World War II, they flew high enough, they all needed to be in oxygen masks. Not pressure suits, but oxygen masks. Okay? So same thing goes when we go down to scuba diving. We don't go scuba diving past, I think the depth of free diving is 90 meters, okay? Which every meter is 3 feet. So think about that depth. That person is insane, okay? Because you got to stop where you need the bends. So anything below a certain depth, they wind up putting everybody in a pressurized capsule. Unless you're the jerk that was trying to show off and go see the Titanic and the cheapest carbon composite fiber Cyclops submarine in your planet, and go poof. You know, when the U.S. Navy heard poof, I think they were checking every hydrophone in the world trying to figure out where their subs were at the point in time. Okay? And they know where their subs are. They know where the Russian subs are. They know where everybody's subs are. And that sub just went poof. It's like, that caused a hell of a problem around all the world navies, I suspect. Okay? But they failed because they went too deep. Okay? And you don't want to do that. But it's only on depth. So that submarine could have been in Lake Superior and been roughly at the same depth when it poof, and as it was in the ocean. The only difference is the density of the fluids, okay? But generally the depth is the only thing that's going to cause problems with this. Okay. Cool. Now where am I going with all this? Pressure at depth. Okay, so all right, this is the sorry, that's surface, not square. Gourmet surface. You know how many times I've written this in my life? Okay. Basically, it's this. W equals specific weight times volume.
I'm sorry, what is the word after F? Exerted.
Exerted.
Oh, sorry.
Volume is the area times Z. Okay. And F becomes W equal to, oops, I'm going to get rid of that, A times Z. Okay. And if substitute pressure in, we get P equals F over A, which will be equal to this times A times Z over A. And we have some fun with the math, and we knock the A's for a loop. Then we're going to get specific weight times Z. Okay. Everybody following along? Cool. Now, the only thing we're going to do with this down the road is the Z will go away, and we'll use the term H for height. Okay. Now, that H could be depth 2. I'm not hung up on it, but we're looking at the change in height. Okay. Which I can put that in here to remind you all, but we'll probably see this. P is equal to specific weight delta H. Okay. But I leave the first one in there because, believe it or not, you can turn that into a calculus equation and calculate the change in pressure. Okay. All right. Everybody good so far? I hate drawing this thing. Just draw it. No, actually, I know how I want to do this. Live smarter, not harder. All right, so if we divide this into subsections, and we wanted to integrate the areas, we could find all kinds of things mathematically, but I'm going to cheat. Okay, we are 1 foot on a side. Okay. At here, we're going to be pressure equal to 4.33 pounds per inches squared. At halfway, 2.165 pounds per inches squared. And then literally here, we're going to be P is equal to 0.4433 pounds per inches squared. So ideally, at different feet down, 1 foot, 5 feet, 10 feet, we're going to get that. Okay. All right, some notes that go with this. A foot square section of water ten feet high contains 10 cubic feet if two Okay, so that's how that all came about. It's not like I made that math up, but if you don't have your books, it's one of those things that explains there. So, anybody lost or confused at this point in time? Ronnie, you good? All right, so one other thing we need to talk about pressure is okay. Now, I know better than make this statement, but it's important to have some basic standard references that we all play with. Okay. Can the air pressure at sea level change? I gotta shake head no. Yes, no, maybe? Cameron, you're looking at it hard. What do you think? Can the air pressure at sea level be different than 14.7?
I'm going to say no.
Okay, we got a hard no now. Just a maybe shaking. What else do you think?
Maybe.
Maybe.
Could change.
It could change.
Maybe it's a safe
Maybe it's a safe answer. Chickens. Cluck, 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 cluck. They're all falling. So the answer is yes. Atmospheric pressure changes around the globe all the time. That's why we have weather fronts. Okay? So 14.7 is absolute pressure at 60 degrees Fahrenheit at this condition, at that condition, specified by the world of whatever. Okay? We just assume it's 14.7 and take it as that assumption. But I want you to be careful that somewhere down your lifetime, someone comes back and says, well, it does change. It does. It could be 14.69. It could be 14.67. It could be 14.8. It could be 14.9. Okay? But high pressure systems, low pressure systems, and they all affect the pressure. Okay? High pressure systems in the atmosphere drive air down to the earth because it's higher pressure. So of course at sea level it's going to be higher. Okay? It's my favorite trick down in the air conditioning lab. I have a mercury barometer. I have a mercury barometer too, but I have a brass barometer. And my favorite trick is to walk by it every day and change the indicator dial to know where it was yesterday. And it changes all the time. I'm probably the only one that actually uses this stupid thing. You know, to the point that I should probably retire with it because no one else may use it. But it can change. Well, we have to have a number that gives us the definition, okay? And you can look it up and get the exact temperatures and pressures and volumes and all that sort of stuff with it, but it changes, okay? Just be aware of that, okay? Now, gauge pressure. Look at this, canoe pressure. I can't even read my own writing. That's bad. All right. We have absolute pressure. Then we have gauge pressure. Yeah, it's not canoe pressure. All right. So it's pressure in excess okay. Now, I don't really like the definition that's used with this one because it could be excess, yes. If the pressure's higher than 14.7, then that will give me my gauge pressures. And I'll do a little math here for you in a second. But ideally, what if the pressure's lower than 14.7? That's not an excess. That's a diminutive loss. You know, what's the deal there, people? So keep in mind, I know the true definition uses the word excess, but yeah, it could be different. Okay. It is a, by convention, so gauge pressure on the top of a body of water, Lake Ontario, Lake Superior, the ocean, will be 0 gauge pressure, but 14.7 atmospheric. Okay, so by convention, there's a new term, hopefully, maybe, well, new term I'm using here today, maybe not a new term you haven't seen someplace else, but what do I mean by convention?
Coming to a consensus.
It's not academic, although the jerks were probably the ones that created it. It's what we use as a standard value. Okay, so we all convened. This is no joke. So somewhere in the world, was a bunch of engineers that got together one time and says, look, we're going to make gauges. We need to come up with a standard number. Can you imagine that debate going on for 3 days? You know, somebody did. They declared it. That's all it comes down to. By convention, we declare it to be this. You could declare SUNY Canton the best college in the world by convention.
So vote on it.
Yeah, let's all vote on it. We could have some fun with that one. Okay. All right. Now, the next bit of this is, I'm sorry, there's a bunch of definitions here. Pressure increases oops, no, I did that wrong. Okay, so the pressure increases linearly as we go deeper. Can you imagine a world in which the pressure increased exponentially as we went deeper? You wouldn't go very deep, you know? Just think about diving into a school pool that's 12 feet deep in the deep end. You know, you'd be crushed at the bottom. You know, no way. So thank God physics actually works the way physics works, or otherwise we'd be in trouble. Okay. All right. P is equal to specific weight times Z only So, no idea what Dr. Regal's little glass bottle is doing up here, but if I fill that full of water and I don't move it, it will be at rest. The pressure at the bottom will be the pressure at the bottom. But what if I start shaking it? Now we get momentum going on in there and the pressures are going to change. Okay? So when we measure this, we assume it to be at rest. Okay? Now, if you find a situation where the body of water is at rest, let me know. It's stagnant and things have died. And it's probably turned green and ugly. Okay? But along with this one wants to come this caveat. When we start dealing with bodies of water, we're going to make an assumption, and I will remind you later on when we get to those points, but assume that the body of water is infinitely large so that we can classify it as static. All right? Otherwise, we're going to be in serious trouble. Okay, that's a good place to stop there. I got a couple more of those to go, but we'll finish. I don't know where my day goes.
Especially like the past couple semesters, I've had my classes like at 10 o'clock.